All right. Here's problem 3.1 from the textbook, and we have to show that the path integral of f dot t, vector field f dot t hat ds, is independent of its path for any central force F. So a radial force, the big thing here is knowing how to write out a radial force. And it's not even that complicated, but something you have to think about a little bit. A radial force, by definition, they mention it in the textbook, is a force that depends on the distance between the two particles, and it always acts on the line in between the two particles. So we have the force, which is a function of the distance, right? So that's the FR. And then we have R hat, which gives it the direction of along the line connecting the two particles. So that's what the force is. And then from there, you just follow the steps in the textbook, and it's pretty straightforward. So you can see that R hat equals X hat and all of that stuff. So we get our equation for the force, and then we can dot it, and you can keep that function outside, and you just have that dot product there when you dot it with t. And t is I hat derivative of x plus j hat dy over ds. I should have written that out somewhere. And then t hat, that's because it's the unit vector tangent to the curve. So in the textbook, they show you that r hat, or that r squared equals that, and then you can sub in, and then you get this right here, down there, and then you integrate that, and we're going to say that when you integrate it, you get some function g of r, evaluated from the first point to the second point. And since when you compute this integral, the answer only depends on the starting point and the ending point, that means that it's a central, that proves that it's path independent. So since we didn't have to specify a path, we know that a force that acts in the radial, radially outwards, only depends on its path independent. I got a little lost there, but it makes sense.